Hi everyone, and welcome to a new episode of Dr. Data Science. It's we talk about different subjects in data science and data analytics, and then today we're gonna talk about time series and then time series use cases and techniques. And we're featuring two of our data scientists today, Adam and David. Welcome, Adam. Welcome, David. Thank you for being here today. Uh,
Thanks for having us.
so so we're gonna talk about a use case you worked on, Adam, and then David also will tell us some notes and techniques about time series in general. Thank you for being here, and let's start with you, Adam. I will add your slides to the stream.
Great. So to start off things, we're going to talk about many ways to analyze time series, but I'm just going to start out with just this one method that is very fast, interesting, and simple. And to do so, I'm going to use a use case looking at baseball's most interesting seasons. So to start, so the method is called Saxon Coding, and it has this pretty convoluted name of symbolic aggregate approximation, which sounds maybe a little intimidating, but it's actually very simple. So it's a method that's used to simplify time series through the summarization of time intervals. And it can be good for dimensionality reduction, anomaly detection, smoothing, and so on. So what it does is it takes this, so you see that there's a time series here on the right,
Mhm.
and it bins things according to equal time intervals, and then gives them a letter grade according to where the average of that time interval
Oh,
is.
and then
So,
uh,
mhm.
do you like during this bidding process? Do you choose how how wide is your window to calculate that average or
Yeah, so all things that are configurable there, so you can choose how many intervals you want to have. They could be equally spaced. That can range from any number. It could be very, very long. Will end up in n sax strings, or they could be very short. And in this case, for the baseball use case, it's actually a lot smaller than you might see for different other type of use cases. And then so that's in terms of the x-axis, but then on the y-axis, you can use a different number of letters to represent your kind of letter grades here. You could think of it.
and your y-axis can be like any variable you're measuring versus time, right?
Yep.
Okay.
Cool. So that's just a little bit on it. Now, hopefully we can help understand this through looking at this one use case. So what I set out to do is find the most anomalous or unique MLB seasons, so Major League Baseball, and trying to see if I could find anything interesting, basically. So I use SAX, and the reason why is because it's very good at reducing the complexity of that analysis and making those trends very easy to find. So to do so, I look at every single season and team as its own time series. So for example, this is the 2000 Anaheim Angels. And this goes all the way back to the 1800s, actually. So there's a ton of time series based upon a team and what their season trend looked like. And this time series is represented by the amount of wins minus the amount of losses at any given point during the season. So if you kind of look at the start here, they started at even, and then they lost a game. They maybe won a couple, down, up, down. And you kind of see that you get these spiky increases and decreases, but there's like an overall trend here. So this is just an example of one of the time series, but we have around 3,000.
And this time
And
series, I'm sorry, this time series what we are looking right now, it's before you do the encoding, right?
yeah, this is prior to all this is just a look at the data that we're going to transform.
Mhm.
And something that's very nice about Saxon coding as well is that it's able to deal with different lengths of the time series. So with baseball seasons back in the 1800s, they only maybe played around 80 games a season, but currently they play almost double that in 162 games. So the nice thing about Sax is that it can handle those equally.
Hmm.
So what the actual method looks like is as such. So here in the top, I have this basically this data frame that contains all 3,000 time series, and this is a normalized data frame too of at any given point of the season after the first game, second game, third game, etc., for all these different seasons. So what SAX will do is it's first going to, according to the number of time intervals that we had specified, in this case, I'm specifying 5, we split each of these rows, each of these seasons into 5 subsections, and then take the average of each of these subsections.
5, that is the window width that you're going to calculate the average to
Yes.
like put these.
Well, 5 equals subsections. So
Okay.
for the times where there are 80 games, it'll do 80 divided by 5 into that's the length of the window. But when it goes to 162 games, it's going to be double that. But what it's really calculating is the first fifth of the season, regardless of the season's length.
Okay.
So in doing that, we see that we can just now only have 5 columns. And in these 5 columns, they're just the average of each of those subsections. So for this first row here, this is the average score that the team had. Then it went down even further, stays down, and this is now an easy way for us to summarize the season. Now, this is called piecewise aggregate approximation, which is another convoluted name maybe, but it's just the summarization into these time windows. Now, so now that we have these numeric representations of these subsections, what SAX does, so the symbolic part of this is that we're now going to assign a letter to those numbers. And in this case, I'm using a dictionary of 4 letters. So it can either fall into A, B, C, or D. And in that, it basically represents maybe whether they fell from the minimum to the 25th percentile, maybe the 25th percentile to the median, etc. But that's also something that's configurable. But essentially, you can just think about it as this was the letter grade for how well or how poor a team did during that time. So for this first row, it's actually, they had a very, very bad season. And so there's 5 straight A's here. And the final thing, the final step of Saxon coding is combining and concatenating those letters together into a single SAX string. So we'll see that this one season can be represented as this one column as AAAAA. And then for this next one, it's maybe BCCC, and that can go on. So, and then for the example that we just saw before, it ended up being CCCC2 for that Angels one. So what's very nice is we've gone through, 162 columns, but now it's only just this one column, and that will retain the information of the entire time series, but now just in that one variable.
So just one thing is not clear to me. So every row is a season here, right?
Mm-hmm.
And the data is like for one baseball team, and then every row is a season. But I'm not sure like what are these 0, 1, 2, 3, 4 columns. So those are like a reduction, but I'm not sure like. Oh, can you explain more about this?
Yeah. So so the season it started maybe in April. That's what it typically does. So the 0 represents what their record was, so their amount of wins and losses after the first game that they played. Then after the second game they played, third game, etc.
Mm-hmm.
And then that kind of gets that graph of the ups and downs that they might have had in terms of their performance.
Oh, so that's basically the 0 to 4. It's yeah, as you said, it's a part of the season, right?
Yeah. If we're looking at this bottom left one, this is now a whole fifth of the season, but done in now one. So this represents maybe the first 15 to 20 games for that top team, and then this is the next window of that time.
And so what SAX is doing basically for every season, it's kind of like giving it a score where that like overall performance in the season, let's say, is like according to the averages.
Yep, that's right.
Okay.
And then it can produce these simple summarizations, and then I can go on and show the interesting results too. So something that we can do with those SAX strings is we can count up the amount of instances where that SAX string occurred. So you'll see that for CCCC, which was essentially just being mostly average throughout the entire season, that was the most common SAX string by far. And then you'll see a bunch of variations of basically being around the average of BCCC, BBCCC. But what's really interesting is once you get down to the unique values, because these unique values, what this is saying is that no other team in MLB history had quite the trends as this one team did. And the way that I kind of confirmed to myself that the method was effective is just anecdotally, just looking at them. So the two that showed up in the unique values were the 2001 and 2002 Oakland Athletics. And if you don't know, like those teams had a whole movie made for them.
Wow.
It starred Brad Pitt. It was a very popular movie. So it kind of shows that this was like movie ready seasons. So in 2001, the A's had the best second half of all time. So there's second half of games. They did extremely well. In 2002, I think they had a 20-game winning streak, which I think at the time might have been the largest winning streak of all time. So you can imagine that it was a very interesting trend that might have been seen. Then there was a 1972 Philadelphia Phillies. This is a pretty interesting one where when Steve Carlton, who is one of the kind of the 5 pitchers that you might see pitch in rotation, when he played, they were 27-10, so 27 wins, only 10 losses, a win percentage of 73%. Without him, they only won 32 games versus 87 losses. So around the same amount of wins, there's a difference of like 70 losses and only like a 27% winning percentage. So a pretty interesting case there. And then finally, the 1914 Boston Braves, which maybe should have a movie made about them. They were in last place on July 4th, around the middle of the season, but ended up winning the entire pennant by the end of the year. So pretty interesting results that like I happened to just stumble into. So you can use these SAX encoding, these SAX strings to do many different things, but it's actually an interesting tool for anomaly detection when you start to look at some of the more unique ones on the list. Here on the right, you can kind of look at, this is kind of the most common, just basically averaging out maybe small fluctuations. And then the most unique, you start to see really wild time series there.
And then,
yeah.
So in the unique values, we're seeing, let's say, like the best performers. And then how about, let's say, the worst performers or like the lowest performance? Is it something that we're going to see also in the unique value section, or it's going to be like?
Well, maybe not. Maybe if it was a uniquely performing team that had maybe a big collapse, because on this slide we saw that this one season was AAAA, and that basically means that they were horrible the entire season. There were that many, they were that much worse than everyone else, and that stayed consistent. Now, what could be interesting, I mean, in this case, the Phillies were an example where they started out being at C, maybe average, maybe a little bit above average. They got worse, got to basically rock bottom, then went up a little bit again, and then went back to rock bottom. So that's what you can kind of think about when you see CBABA. Like you can kind of get the gist of what happened very quickly now, and just in that one SAX string representation.
Mm-hmm. And then I have a question about the implementation. Are there any, let's say, ready-to-consume packages where you can implement SAX algorithm, or you need to kind of like write everything from scratch?
Well, in terms of so in our TIBCO Data Science Team Studio product, there is a Saxon Coding operator that I use to help create this. I can also say from experience that doing this in Python, because it's so simple, it's not even required to maybe even have packages that have models pre-trained, something like that. Instead, it's simply about binning sections, assigning grades according to different bins as well, and then you can kind of create it on your own too.
Right, but I just would mention that
Mhm.
when you have a very large data set, it is helpful to have something like the typical data science node, because that I believe parallelizes the logic, and is very efficient.
Yeah, and that's kind of what I'll turn to just as my final slide here, just to show an example of a different application. And this is using Saxon coding for noise reduction. And this is actually a case that was used in typical data science, where this time series, which was very long and has a bunch of small fluctuations, but you'll see that there are kind of big anomalous sections here. But using Saxon coding, we can reduce the number of variables needed to store all this information, and then basically smooth out that curve. And in doing so, you can see that we got rid of all those little spiky fluctuations on the time series, and instead just captured the bigger, more prominent trend.
This is interesting because I can see like I might be able to use this in a couple of oil and gas use cases because we have a lot of like long and noisy data. Uh,
Mhm.
my question is, so when you do this reduction, do you or like is there any way to know the let's say the main variables that contribute to the variance or like yeah
Um,
I
I
know
think
this.
that it would probably have to require some other method on top of it. I don't think Sax itself would have something that obvious. But there's certainly things you can try to do when you look at maybe multiple variables at once to try to tie the two together. But
Yeah.
in my experience with this, it was just that single univariate use case.
Hmm. Interesting. Nice.
Yes, and that, SAS encoding is usually configured for a univariate. Have you ever seen a multivariate version of SAS?
No, but it would probably be pretty interesting. I'm sure that there are ways that you could
No.
try to incorporate the two of them.
Cool.
Interesting. Okay.
Cool. So yeah, that's all I have just for Saxon coding. But now I'll turn it back to you, and we can get into some other methods of analyzing time series.
Thank you, Adam. Yeah, that's interesting. I think I'm gonna try this in one of my use cases and then see how it goes.
Great.
So now we'll turn to David, and then he will talk to us about some use cases and notes and time series. Let's see.
All right. Can you see my screen?
Yes, yeah, we can see it.
Oh, okay. So my name is David Katz. I'm a consultant at TIBCO. I've been with TIBCO about 10 years and done a variety of things. But I just thought that for this talk, I'd start out with a demo of doing Holt-Winter's um, modeling, time series modeling within Spotfire, which turns out that even though I've been working with Spotfire for a long time, I've never done exactly that. So I thought it was interesting. I could talk about some of the issues that come up, irregular time series or date formatting issues and so forth. And then as there's time, I'll talk about different types of time series models, cross validation, which validating models is a particularly important aspect, and then an entirely different approach, which is for subsequent similarity search, which actually, while Adam was talking, I realized that there are similarities as well as differences in those techniques. So let's start with Holt-Winters, which is a family of time series models. It's implemented in Spotfire, for example. It's every data data science, from R to Python and everything else, does have versions of this. And basically what it does is it combines exponential smoothing and periodic or seasonal variation. Exponential smoothing sounds very fancy, but really uh, a form of weighted average
Mhm.
for a moving average and so forth. There's also, continuing on the idea that there's different variations on Holt-Winters. It's important to understand that there's both additive and multiplicative versions of the model or parts of the model. There are damped versions, which means that as you project into the future, you move the trend more towards linear, so that you don't get wild fluctuations. There are robust methods and so forth. The basic idea of Holt-Winters, as I mentioned, really is combining the uh, the trend with the seasonality. Uh, this is the recursive equation. I'm not going to go into the math too much, but I think that what's interesting about this is you see that it's a recursive um, type of thing. So at any point, you look at the data up to that point, and then that gives you the information you need to make a forecast for the next point. So let's open up Spotfire just for a second, and I'll just open up a very simple um, um, time series, open source time series data set, and of course it shows us what that looks like. It just has a date and sales. And in the interest of time, I won't go down all the rabbit holes that I encountered when putting this together, but I would just point out that if you look carefully at um, the date column,
Yeah.
It's not in month, day, year format, right? It looks like it's the first of the month always, and then it's um, the month is second, which is common in Europe.
In Europe, yeah.
In order to do this, uh, the easy way, and not go down a lot of the rabbit holes that I found, you could find something, if you happen to know how they do it in New Zealand. I happen to know in Great Britain, this is what they do. And so by saying the culture is Great Britain, Spotfire gets the hint. And actually, if you then also tell Spotfire that it's a date, uh, it'll do a good job of ingesting that and creating a data set. So the good way to start, of course, is to create a visualization.
Mhm.
Uh, here's the date. Uh, it's typical Spotfire thing where it
Yeah.
cleverly makes different levels of a hierarchy, and then you have the retail sales. It says sum of retail sales by default, but since there's only one observation per time, it really doesn't make a difference if you take that summation away. And this is really interesting because even though it's used car prices or used cars total sales, you see a couple of very interesting events in the time series. So you've got the start of the financial crisis,
Yeah, so you can see that as well.
and of course the start of COVID is right here. So those
Yeah.
two things had a unusual
Events.
effect on things, and um,
There's an overall trend. You can see it like an increasing trend.
right. So again, if you focus in on before these shocks, I just wanted to mention that these kind of events are often called shocks in the time series papers, and some packages allow you to include that in the modeling. Spotfire tends to not do that automatically, but of course you can always use a data function. Or, well, what I'm going to do right now is to just take this part of the time series where you don't have a shock,
Uh-huh.
and say, well, let's do a model there. So one thing I found is that although Spotfire has this option for Holt-Winters time series, it's not obvious where to find it. You look on the menu, you don't really find it anywhere. But you, it's thought of here as a type of visualization. So you go to lines and curves, and you say you want to add a certain type of lines and curves, and there's the forecast for Holt-Winters. Now this alpha, beta, and gamma appear in that formula for the recursion, but you don't have to specify them. The fitting, Spotfire will automatically find the best starting values or the best parameters, I should say, to make these work. It's also lets you choose simply between additive and multiplicative models, which just simply means that those recursive equations, instead of having adding up these different components, you multiply them and say, okay, and often you do see that if there's wide variation, the seasonality is best modeled by a percentage. And so, for example, you might say in June, sales are 10% higher, so rather than $100,000 higher, something like that. So that lets you uh, put this together. You can specify the frequency. You can say, oh, how many time points ahead do I want to forecast? And do you want to show the confidence intervals? And so it really is quite simple. You find that the second uh, line in your chart is here, um, uh, just specified in a different color.
Yeah.
Um, One thing I actually meant to do was uh, filter to the marked curve so that now it does the same analysis on just the subset, which is very handy. And then these out here, here's the predictions for the future, and here's the
The confidence interval.
95% confidence interval. So that's a quick introduction to the automated feature for whole winter forecasting in Spotfire.
And then and Dave, like for a time series like what we are looking at right now, it's like
Yeah,
always increasing. Is
yeah.
it uh, do we go with a multiplicative model, or we go with an additive, or that doesn't like yeah, that doesn't, let's say, help us in deciding?
Well, in terms of a nonlinear trend, that's something I don't believe would be handled automatically in Spotfire. The assumption here is that there's a linear trend that then is superimposed on a moving average or an exponential smoothing component. So, if you had something that had a fluctuating trend, you probably would have to use something like the profit package, which is in R, or there may be a version in Python.
Yeah.
Not sure. So that gets you into using a data function in order to play around with that. Um, as far as multiplicative, making that choice between a multiplicative model and a additive model, the simplest thing is just to try both. Try one and the other, and you see which appears to give you the better fit on your existing data, and then you could use that to try and uh, project forward in time. Um, So let's talk a little bit more in general. I did the demo. I also find that when you look at this, you sort of wish you could do a validation where
Yes. Yeah.
you could see the other, see the actual
Yeah.
plotted alongside the forecast, right? So here
Yeah.
you have the forecast and the confidence interval, but you don't, you would have to do a separate plot or go through some effort. One thing that's nice is that there's a nice article on how to use Iron Python within Spotfire to retrieve the forecast, and then you can plot it in conjunction with the actuals.
Oh, okay.
So that's something you might want to do. Okay, so let's take a few minutes to switch gears and say, in general, different types of time series models. So often you want to, the simplest idea is to forecast values, for the next day, the next month, the next week, whatever you have. So there you have tomorrow's weather as an example of a one-step forecast. But often you want to look, on your phone, you can see a forecast for the whole week. So that's a slightly different type of model. So actually, there are four strategies that are widely used. There's a nice article by I forget his name, but he's written a lot of articles about this. But basic four-step four strategies rather. So you can do the direct multi-step forecast. So you just build a separate model for one for each day in the future, or you can recursively apply your model once you've forecasted one day. Now you have some artificial data, and you can recursively apply that to get the previous results. That's what's done in Spotfire. You can also combine these methods where you use the output of a direct model to then create model 2, and doing it in those two steps helps smooth out some various problems. And of course, now you can use a deep learning type of model, and you just have multiple outputs, multivariable regression.
For the recursive multi-step, so do you keep forecasting, let's say, the next step using also the forecasted like data that you just like had?
Yes. In other words, the recursive formula that I showed and that's used in the simple Holt Winters model, it just says, to calculate today's forecast, you look at yesterday and maybe n days back.
Yeah.
Right. And so, but that only gets you one more day. So now, if you want to know what's going to happen tomorrow, you can use your forecast for today as data. You turn around and use your forecast as data, and that's the recursive method.
Mm-hmm. Okay.
There's also Rob Hinman is kind of the guru of time series, and he has a lot of great material on the web, and I highly recommend that. He points out that the recursive approach can sometimes be biased depending on the type of model, and he has a R package and method that he calls rectify. So he takes the residuals from the first model and builds a second type of model on the other one. So that's a very interesting approach, which I recommend. And how are we doing on time? Should I go ahead, or you need?
Yeah.
Okay. So cross-validation, probably most of the audience is familiar with the concept in regression, but it's not obvious how to use cross-validation with time series. You can use Hinman's method whenever the predictors are lagged values of the response. One gotcha is to get the lagged values first before splitting it into your k-folds for cross-validation.
Okay.
And this is good with multiple predictions. And the problem is that if your time periods overlap, you can get overfitting. So let's look at a simple train validation test. Rather than split the data by random, it makes more sense with a time series to say that here the green is your time period for training.
Yeah.
And then lilac is test, and then finally validation. Or sometimes the terminology is the other way around. So this is one nice way to do it, but this just gives you one test sample. right? So one trick is to get multiple error estimates by doing a series of time series models. So here the blue is for training, and the outcome, the one step ahead outcome, is in red. And so the first row is one model, and you can see how well it predicts. And here the second row is a separate model, and you can see how well it predicts on this different time period, and so forth. So this is a very clever method for getting multiple models that help you see how consistent your predictions are, and actually give you some
But
another way to estimate
but
the
don't,
variance on your
but don't you
estimation.
think, David, that the length of the training data will affect the accuracy? For example, if we look at the first like series, and then we compare like with the last one, there's like a large difference in terms of the amount of the data that we're training on. Will that
Yeah,
affect?
that's an excellent point. And you could also, if you wanted to correct for that, you could drop off this first blue dot in the second series, right? So that it'd be more consistent.
Okay.
Uh, this is one way to do it. To say that, yeah, you probably will observe that you can do better with a longer time series, as long as you're not getting into shocks and outliers in your training set.
Yeah.
So that's uh, useful. Of course, if you want, 4 steps ahead, you would just modify it that way. That's pretty clear. Um,
And
and
when you say 4 steps ahead, are we predicting like the 4 steps values, or are we predicting like the value after like the 3 steps? So it looks to
Yeah,
me
so
like,
in other words, if these are quarters, you might want to say, well, what's my prediction for next year in the same quarter, right?
oh,
So
okay. Hmm.
that would be an example with four. But
That's
the
interesting.
numbers just depends on your application, what you're trying to do, and that goes back to that list of different strategies
Hmm.
for doing the modeling. Um, So just a note that, if you're an R programmer, there's this nice package that makes it easy to do this type of time series cross uh,
TSCD.
cross validation. Um, Here's a use case back at the beginning of the pandemic. We were looking at a lot of different ways of kind of projecting the future, without going into complex epidemiological specialist kind of models. We were just trying to do what we call nearcasting, is just trying to do what's going to happen in the next couple of weeks. Um, and one one way you can improve just on a moving average, the New York Times and other sources, they're very fond of the moving average, which has a lot of advantages because it's easy to explain, it's easy to understand. A super smoother is a little more sophisticated, but it's basically the same idea of using the lagged variables,
Hmm.
to do an adaptive regression model using polynomials. Uh, you can also do GAM modeling. I tried to do that just using longitude and latitude, but what we found that wasn't very effective. So one thing that we did was try to do uh, methods for generalized additive model. So this would be a Poisson model, a count of new cases, and you uh, because it's a GAM, you need to estimate the smoothing parameter, and we got some fairly decent results using that. So you see, here's the first half of this data set, which is just this small population, and you have counts per day, which as we know, those are very noisy. Um, and what we did is we split the data that we had at the time and just built a model on here. The robustness helped us with these points, which are likely from reporting anomalies where they maybe don't report everything each day, but end up aggregating them and catching up after a while. But it was actually possible to get a fairly, as the number of cases increased, this proved out to be within the calculated confidence interval. So that was kind of satisfying even in a bad situation. And this last thing I could talk about is the similarity search, which basically is used for things like anomaly detection or finding common patterns. So as you can see, it has a lot in common with Adam's application of the Saxon coder, but it's just based on different principles, and it handles things a little bit differently. I think I duplicated that slide. And basically, it creates a matrix profile which annotates a time series, right? It adds some information to a time series, and it looks like this. This is an example of an application where you're looking at a time series that kind of has two modes. A mode that's very frequent and a mode that's very unusual, right? But when it happens, it's very similar to these other ones. So the idea of the matrix profile is to create this blue line, which says, okay, well, these all look very similar to all the other ones, right? In terms of the correlation that's used, you have maybe a subsequence of 100, and you compare that to all the other subsequences of 100, and it's very similar to most of them. But if you ask the same question about this, it's pretty rare that you find something that's similar. So this subsequence is it's different from a lot of what you see. So that's what gives you the matrix profile, and it gives you a kind of a summary of how unusual this subsequence is.
So what is our y-axis here in the matrix profile represents? Does it represent like?
Well, in the matrix profile, it's just a correlation on version of the original time series. So you go through and you normalize the two subsequences, and then you take the correlation between them. So basically, it's a correlation. It's how much is it correlated with all of the other. Well, since you asked, I'll go into it a little deeper. You're doing a huge matrix, right? You're comparing every subsequence to every other subsequence.
So we're basically kind of like creating a distance matrix.
Exactly. It's a distance matrix, but it's so huge that you just save the outliers, right? You just say, well, which of all these correlations, which is the lowest, right? So now for each one of these, you can say, well, the lowest correlation is pretty high, but the lowest correlation for these is very low, right? So this is not correlate. This one is not correlated with hardly any other subsequence. There's a couple, but mostly it's just it's rare. So this is very analogous to Adam's just taking the frequency of the different SAX patterns. This is instead this does this virtual distance matrix and picks out the smallest correlation. And when the smallest correlation is really low, that's an outlier.
Mm-hmm. And then
So I want to leave time for you there.
Yeah, I have one last question about this because this is very interesting, and I was trying to use it in one of my oil and gas applications. My question is, because I face this a lot. How does this perform when we have a large data like time series? Let's say I don't know, like close to million rows, or sometimes like I deal with data of like 1 month and then it's sampled in like 1 second. Uh, does it like experience some slowness or something or?
Well, it performs very well compared to other methods for subsequence search, right? So if you're doing a search, either a matrix profile like we talked about, or a search for a particular pattern, sometimes you might have a known pattern and you're looking to see if it shows up in this sequence. In those cases, although it can take some time, it's a lot faster than a lot of competing techniques. Um, uh, it's because it's been developed to use a lot of tricks. So as you slide the window to look at different subsequences, uh, you can compute the correlations in an incremental way. So
Mhm.
in R, the package is called TSMP,
Yeah.
but you can Google for, there's a couple of different terms that are used for this. MASS is Maureen's algorithm for subsequence search, or you can look at um, uh, matrix profile, and you can find a lot of material on it. And there are variations where they try and do um, time morphing, so that a sequence that's longer can still be matched with one that's shorter, which the basic algorithm doesn't handle. So there are a lot of uh, there's a lot of research been done in the last.
Yeah, I think I've seen a similar implementation in Python with the same name, the TSMP.
Yep.
One last question on this: can this method be used to classify, let's say, uh, can this method be used to classify the time series? For example, if I'm looking for specific sections of the time series, if I'm looking on these like rare events, is this method a good candidate to do that?
I think it is. I mean, we can talk about it offline, but
Yeah.
basically, searching for outliers in a one-dimensional or even just a low-dimensional collection of time series. This is a very powerful technique.
Okay. All right. Well, thank you, David. That was very interesting topic. I mean, yeah, I was looking forward to hear, yeah, about the time series because most of the stuff I do, they're like time series and long time series with noise. Um, I'd like to share with you the work I did in Shell AI Hackathon. So basically, this was a hackathon that we kind of like jumped in late, so we didn't have a lot of time to test several methods. But basically, the problem statement is we were given 1 year worth of data of some solar sensors, so and then some solar and climate sensors. So you're given, for example, the humidity over 1 year, the percentage of the clouds, temperature, and then other couple of variables. And you also given a test data of 6 hours, and then you are required to predict the cloud coverage basically for the next 30 minutes or 60 minutes or 90 or 120. So they want you to predict the cloud coverage in kind of like four categories. And then one of the conditions is you don't consider these test data kind of like a continuation for the 1 year data that you were given. So those are like two different things, but you're gonna use the 1 year data just to train your model. So I did all the work I did in here was in Python. We didn't have the time to like transfer that to Spotfire. Uh, we did some of the some data exploration, and this was the distribution of the night. So, for example, they have a camera that takes pictures, like sky camera, takes pictures to the sky to kind of like help you to calculate the percentage of the cloud. And then when it becomes night, this camera will return -1. So I just like plotted this here just to see, just to like validate the data. The data also suffers from a lot of missing values, and then there's like a lot of missing values in the middle of the year. I also looked at the correlation between the variables, and then I found out a couple of interesting correlations. So basically, there is the dry bulb temperature. It has a good correlation, or like a relatively good correlation with the percentage of the cloud, and then a couple of other variables. But overall, there's no strong correlation. I mean, the maximum I was looking at it was like in the 60 something. Within the time limit that we had, I followed an LSTM approach. So basically, I created a couple of lag variables depending on the category that I'm predicting. For example, we were giving 6 hours. So we were giving 6 hours, and then they want us to predict the next 30 minutes. So these 6 hours over 30 will be like 12 steps. So those are like these are the numbers of the lag variables that I created. One of the complexities of this problem is we are dealing with multiple variables and like multiple time series to predict the cloud coverage, and then that was like something new to me when I worked on, because the previous problems that I worked on, they were like one variable over time. But in here, like you're dealing with, for example, the temperature, the humidity, the wind, and then you're creating lag variables for all these multiple variables to account, or like to kind of like predict the cloud coverage. So what I was looking like at the literature, and then there was a lot of recommendation on using LSTM, because one of the issues that the neural network suffers from is, they call it the vanishing gradient. So as the learning process continues, the gradients will be close to zero, and that will not add any new information to the weights when you update them, and then you're kind of like reach to like a plateau period. And then the other feature of the LSTM is kind of like regaining the information over time, not like the normal neural network. So long story short, we were able to achieve 83% accuracy within like it was like a 1 week deadline of work. And then my final thoughts were I was trying to I was willing to like test other methods, or maybe like test other variables, or like subset of variables, but that was like that was the all what I could do in this hackathon. Yep. So that's it for me. Thank you so much for being with us today, and we'll see you later. Thank you so much.
Thanks, Athir.
All right. Thanks. Goodbye.